All right, so today we're going to talk about linear equations again. We're going to kind of build off of what we were doing last class. Here's today's plan. We're going to get a lot of review today of one-step linear equations. Then we'll apply these types of linear equations to real-world examples. So in other words, word problems. Don't worry though, these word problems, they'll hopefully be pretty straightforward. Things don't really get too crazy with this, at least not early on. But lastly, we're going to move on to two-step linear equations. So in order to have any success with those two-step linear equations, you need to have mastered the one-step ones first. Anyway, I'll stop rambling. Let's roll. So just a little bit of a reminder, solving linear equations. The entire point of this unit is to solve for x, right? This requires us to rearrange equations to isolate x, in other words, get x all by itself. Now, to isolate x, we need to undo anything that is happening to x. So this involves using opposite operations. So if something was multiplying x, you'd have to divide. Or if something was dividing x, you'd have to multiply. Or if something was adding to x, you'd have to subtract. And if something was subtracting from x, you'd have to add. So remember, just whatever you do to one side of an equation, you have to do to the other side. This is because an equation is kind of like a balanced scale. Whatever you do to one side, like if you remove something from one side, you have to remove the same amount from the other. So we'll start with a really basic example. 5x equals 60. This means 5 times x equals 60. So we need to do the opposite operation of whatever is happening to the x. Notice x is being multiplied by 5. That means we have to do the opposite to that. Let's divide by 5. And whatever you do to one side of the equation, you got to do to the other. So to get x by itself, we just did the opposite operation. We're dividing by 5. That's going to knock these guys out. And then we're going to be left with x is equal to 60 divided by 5. Well, 60 divided by 5 is just 12. So x equals 12. So types of linear equations, we've done 3 different forms of linear equations so far. We've looked at ax equals b, x divided by a equals b, and a divided by x equals b. This one in particular was the most challenging, but these other 2 are what we'd call one-step problems because you can solve them in just one step. So let's look at this one first. Negative 15x equals 75. Well, to solve for x here, we have to do the opposite operation of whatever's happening to x. So let's divide by negative 15 on both sides. That's going to knock out the negative 15 here, and we're going to be left with x equals 75 divided by negative 15. If you need to use a calculator, by all means, go for it, but that's going to equal negative 5, because a positive divided by a negative is going to be a negative answer. As for this next one, x divided by 20 equals 3. Well, once again, we got to do the opposite operation of whatever's happening to x. So let's multiply by 20 on both sides. That gets rid of a divide by 20, of course. So in other words, x is going to equal 3 times 20. Well, 3 times 20 is 60. Last one here is the most challenging. When there's an x in a denominator, you actually end up having a two-step problem. We really hate having an x in a denominator. It drives us up the wall, it just drives us bonkers. We don't want this, right? We got to get rid of that. So to get rid of that x in the denominator, what I'd advise you to do is multiply it by both sides, right? So in other words, just as if this was like the 20 in the last example, if you multiply by x on both sides, that gets rid of the x that's in the denominator. So watch what happens. This is going to become 40 equals negative 4 times x. That becomes a lot more familiar. That looks a lot more like this very first one we did here today, right? So in other words, to get x all by itself now, we just got to divide by negative 4 on both sides, right? So negative 4x divided by negative 4, that'll cancel those negative 4s out. This is going to leave us with x equals 40 divided by negative 4, which is actually going to be negative 10. Perfect. So if you're ever wondering if you got it right, you can always take your answer and go back to your original question. You could try 40 divided by negative 10. Good news is 40 divided by negative 10 is indeed negative 4. So you can always check your work that way if you're not certain whether or not you got it right. All right, so I want you to try these on your own. What that means is please pause the video right here, get out a piece of loose leaf paper, just jot them down, give them an honest shot. Pause the video here and I'll go over them in just a second. Okay, so hopefully you went over these on your own. Let's just check to make sure you did them right. For this very first one, we've got to do the opposite operation of whatever's happening to the x. Notice x is being multiplied by 8, so do the opposite of multiply. Let's divide by 8. Divide by 8 on both sides. You're going to have x equals 88 divided by 8, which is 11. That one is done in one step. Same with this next one, x divided by 70 equals negative 5. Let's times by 70 on both sides. This is going to give us x equals negative 5 times 70. I believe that's negative 350. And as for this last one, it's going to be a two-step problem because x is stuck in a denominator. So let's multiply by x on both sides. This is going to give us negative 30 equals 15 times x. And then, of course, we just have to divide both sides by 15. Boom, boom. And that's going to leave us with x equals negative 30 over 15, which is negative 2. And I didn't mention in the last slide, I think I mentioned it in the last video I made on this. Just always note, I like writing my x on the left. Like you notice I didn't go like negative 2 equals x. There's nothing wrong with that. If you had said negative 2 equals x, that's totally fine. I just prefer, just out of convention, I like putting the variable first. But again, it really doesn't matter. That's the whole nice thing about an equal sign. If the left side equals the right side, you can switch them around. It means the same thing, right? So if 2 or negative 2 equals x, that's the same thing as saying x is negative 2. Hopefully you get that. Don't worry about it too hard if you don't. Anyway, moving on. All right, here's a word problem. So, of course, I was talking about a real world situation, and now maybe I'm kind of like eating my words here. I don't think this is a very good real world problem, but here we go. Anyway, Brooke is thinking about buying a parachute. She goes to the local Parachutes R Us store. Those are found in every town these days. To scout out prices. She finds a parachute on sale for 30% off with a sale price of $560. What is the regular price? Write as a linear equation. So we did a question like this before the lockdown. Not a parachute one, of course. I don't remember what was in that one. I think it was a Bob Ross painting or something. And there's kind of a trick to this. You're taking 30% off the regular price, okay? 30% off the regular price is the same thing as saying 70% of the regular price. Okay, be careful with that. I know there's just an extra F on the word off, but it is important. 30% off the regular price is the same thing as saying 70%, that's 100% minus 30%, 70% of the regular price. Now, the reason this is so important, the of word, is because in math, generally speaking, the word of is going to mean times. So 70% times the regular price equals the sale price. Okay, this is already like a skeleton for our linear equation here. Let's see how this could work. 70%, well, we can't really write that in an equation itself. We don't like using percentages in equations. Percentages should always be decimals when they're actually used in math. The only reason percent is a thing is so it's easier to communicate. But 70% is 0.70, right? Of the regular price, so that means times, we'll put this in brackets because we don't like using the time symbol anymore, times by the regular price. Why don't we call the regular price R? I mean, you could call it X, whatever you want. I'll just call it R though for regular price. So 70% of the regular price, so times by that regular price, equals the sale price. Well, the sale price we know is $560. So I might as well just say 560 rather than writing like S for sale price. I'll actually use the real sale price here, 560. So we're looking for the regular price, okay? This is the linear equation that we've set up. The linear equation, right? So it's just something times something equals something. It's a linear equation. Matter of fact, it's like an AX equals B type of linear equation. If we're going to solve for the regular price here, we just need to undo whatever's happening to that regular price. Well, the regular price is being multiplied by 70%, in other words, 0.70. So to get rid of that and get R all by itself, let's divide both sides by 0.70. That'll knock out the 0.70 on this left-hand side here, and we're going to be left with R equals, oops, I don't know why I did that. My mistake, hold on, there we go. R equals, let me bust out my calculator here, 560 divided by 0.70, and I get a very nice round number here, $800. So a way of checking your work here, I guess, would be to say, all right, does that seem realistic? The original price being $800, if you took 30% off of that, which isn't not even close to half, somewhere between like half and 25% off, does that seem realistic? Well, personally, I think it does, because half off of $800 would be $400, and our sale price was actually $560. So it seems pretty realistic to me. I guess the moral of the story is here, when you see the word off, We don't really like that too much. We'd prefer to change it to be something of. So you just kind of have to flip your percentage around. Instead of 30% off, think of it as 70% of. So whatever makes it add up to 100%. Yeah, I think that's pretty much all I can really say about that one. Let's move on to another example here. So Cole walks into the PAT knowing he needs at least 40% to pass. Good news for all you guys. PATs apparently aren't happening this year. So yay, there you go. But hey, Cole walks into PAT knowing he needs at least 40% to pass. He's told that the PAT is out of 70 marks. How many questions does he need to get right? Right as a linear equation and solve. Okay, so we know it's out of 70 marks. Probably pretty easy to just start by saying it's something out of 70. We want to know how many he needs to get right. So that's going to be x out of 70. And this has got to equal at least 40%. So 40%, again, you can put that as 40% right here, but we don't like using percentages in math itself. So we turn it into a decimal, 0.40. So x out of 70, some amount of questions correct out of 70 questions in total equals 40%. We just need to solve for x. This is already our linear equation. So we're already good to go there. So to solve this one, we just need to times by 70 on both sides. This is going to give us x equals 0.40 times 70, and that is going to be 28. So in other words, in order for Cole to succeed at his goal of getting at least 40% on this PAT, which is the minimum he needs to pass, that just means he needs to get 28 out of these 70 questions correct. Now, again, disclaimer, I know Cole's probably shaking his head right now. This isn't accurate, of course. Right? I'm not saying Cole actually is. I'm not using anyone's marks. I just threw a name in here. So don't worry about it. Don't worry about it. I'm just teasing. Moving on. Next question. Zari got an assignment back and found she got 92% on it. She sees that she got 45 questions right, but because of Mr. Scott's hieroglyphic chicken scratch writing, she can't tell what the assignment was out of. Use a linear equation to find out what the assignment was out of. So here's what we got to think of here. This one's going to be kind of like the one we just did about Cole. She knows she got 45 right, but doesn't know what it was out of. So we can say it's 45 out of x. But she knows that's going to equal 92%. Now remember percents, we don't like percentages. We have to turn that into a decimal. So that's going to be 0.92. Now we have to solve for x. Notice how as soon as you break it down and write it as a linear equation, it stops being this big scary word problem and just starts being a regular old math problem that we've been solving this whole time. So again, how I saw it was she got 45 questions right. So that tells me it's 45 out of something equals 92%. So if we're going to solve for x here, we just need to times by x on both sides. That's going to cross it out there, and it's just going to stick it over there. So 45 equals 0.92x. And then we have to divide by 0.92 to get x totally by itself. Yoink. And this is going to give us x equals 45 divided by 0.92. And this is where things get a little bit weird. When I threw this in my calculator, here's what it gave me, 48.913, and then a bunch of other stuff. Well, clearly this test isn't out of 48.913. So we kind of have to deduce something a little bit different here. It wouldn't be really, I shouldn't say it wouldn't be possible. It just wouldn't be practical for a test to be out of a weird number like this. So let's actually say the test was actually out of the nearest number to this, which would be 49. And probably worth noting, if this test was out of 49, her score was 45 out of 49. If you actually check what 45 out of 49 is in your calculator, you would see it's actually 0.9183. And then I guess that would round up to 7. So in other words, that'd be 91.837%. If you actually did get 45 out of 49 on an assignment that I gave you, that would actually end up rounding up to 92. So yeah, the math does check out here. She must have gotten 45 out of 49 on this assignment. All right, hopefully that's making some sense here, guys. I know this is kind of a weird medium to be teaching this under, but if you have any questions, make sure you're contacting me in Zoom. All right, so here's some new types of problems today. The good news is these are only another additional step to it. It's the same general idea. We're solving ax plus b equals c type problems today. So the linear equation in this form is what we consider a two-step problem, obviously, because there's going to be two steps to do this. But the question that always comes up is, what do we do first? Just keep in mind, since we're undoing an equation, we have to follow the reverse order of operations, or in other words, reverse BEDMAS. So that means is if we're trying to get x all by itself, we have to undo everything. We have to work backwards. So we need to start with our addition and a subtraction, and we have to work backwards to get to our brackets. BEDMAS is used for actually solving what something is equal to. Backwards BEDMAS, or reverse BEDMAS, is used for undoing everything to solve for a missing variable. So this tells us we need to undo our addition and our subtraction first, then worry about our division and our multiplication, then do our exponents and our brackets last if necessary. So if we're going to start with this equation, 5x plus 2 equals 22. We're trying to undo everything and get x all by itself, so we should use reverse BEDMAS to start picking this apart. Reverse BEDMAS tells us we would need to start with the addition and subtraction. So in other words, notice it's 5x plus 2. That's what's happening to the x. Let's get rid of this plus 2 by minusing 2 from both sides. This will leave us with 5x equals 20. And now it just becomes a one more step problem. Let's just divide both sides by 5. Yoink, yoink. And we've got x equals 20 divided by 5, which is 4. Okay. Moral of the story here is undo your addition and subtraction first, then worry about your division and multiplication next. And if you're ever curious if you got it right, you can always just take x as 4 and plug it back in this original equation. So 5 times 4, which is 20, 20 plus 2, that's 22, right? So it works. Moving on. Let's do a few examples here. I would actually really appreciate it if you guys paused the video here and just gave these questions a try on your own. You can compare your answers to what I do in just a second. All right, so I'm going to go over these right now. 10x plus 4 equals 104. We need to use reverse BEDMAS. Let me write BEDMAS at the top here. BEDMAS, we're going backwards because we're trying to undo to solve for an x. Start with your addition and subtraction. What's happening to x? Well, it's being multiplied by 10 and added 4. So let's minus 4 from both sides. This is going to give us 10x equals 104 minus 4, which is 100. Then we have to divide by 10 on both sides. Boom, boom. And this gives us x equals 100 divided by 10, which is just 10. All right, next one, negative 3x plus 4 equals negative 8. Let's start by getting rid of the addition, so minus 4 from both sides. This gives us negative 3x equals negative 8 minus 4. Be careful with that. That's actually going to be negative 12. Then we have to divide by negative 3 on both sides. So if we divide by negative 3 here and divide by negative 3 here, you're going to see that x equals negative 12 divided by negative 3 is positive 4. Last one here, 9x minus 2 equals 70. Just add 2 to both sides because, of course, addition and subtraction have to be removed first. This gives us 9x equals 72. And then just divide by 9 on both sides to get x totally by itself. So x equals 72 divided by 9, which is 8. All right. And, oh, yes, here we go. So next up, we got when fractions get involved. That some of your hearts just dropped on this one. Don't worry, don't panic. We've dealt with fractions before, but let's just see some sort of a strategy that we could use to get through this, right? So remember, in order to add or subtract fractions, they must have common denominators. So if you ever have to add or subtract fractions over, you got to just change them so they have common denominators. We'll see a few examples like that in a bit. To multiply fractions, this is the nice one. When you multiply fractions, you just multiply the numerators, and then you multiply the denominators. So in other words, you just multiply straight across. If you find that you have to divide fractions, however, keep the one being divided. So the one that's sitting on its own all by itself, that one stays the same. Change your problem to a multiplication, and then flip the one that's actually doing the dividing. So if you're dividing away something, that something is the one that actually has to flip. So let's look at this for an example. 2/3 times x equals 4/5. Okay, 2/3 times x equals 4/5. Well, since it's 2/3 times x, we should divide by 2/3 on both sides. Now, dividing by 2/3 on the left here is just going to get rid of the 2/3. That's the whole plan. But notice on the right, we have 4/5 divided by 2/3. You guys know the old song that we had, right? Keep, change, flip. Keep the first one, 4/5, change 2 times, flip 2/3 to become 3/2. Keep, change, flip. Yeah, that's the action. All right, anyway, moving on. So x is therefore going to equal 4 times 3, which is 12, over 5 times 2, which is 10. So x is equal to 12 over 10. But you could do one of two things to this. You could simplify it, of course, because 12 over 10 is not a simplified fraction. You can divide both the top and the bottom by 2. So that becomes 6 over 5, right? So 6 over 5 is a perfectly acceptable answer. Or if you are more this kind of a person, maybe you prefer just to have your answer as a decimal. I really don't mind. I don't care if it's a decimal or not. Your textbook probably prefers keeping things as fractions, but whatever floats your boat, right? So 12 divided by 10, that's the same thing as saying 1.2. Generally speaking, if something was given in fractions, you probably should put your answer in fractions. But in this case, 1.2, that's not that bad, right? It's not like it's a repeating decimal or anything. That's a pretty safe answer as well. All right, we're going to do a couple two-step fraction examples. Make sure you copy these down into your notes, but again, I'll show you how to do these ones. We want to solve for x. So that means we have to use reverse BEDMAS to get x all by itself. So the first thing we've got to do, get rid of any addition or subtraction. So we need to get rid of this plus 1/2. Best way to do that, of course, is to minus 1/2 from both sides. Boom, boom. That's going to leave us with 3 over 6x equals 2 over 2 minus 1 over 2. Well, when you minus fractions, you only subtract the top. The bottom stays the same. So 2 minus 1 is 1 over 2. 2, it's just 2, right? You don't minus the denominators, okay? So 3 over 6x equals 1 over 2. To get rid of this 3 over 6 here, you need to divide by 3 over 6 on both sides. But dividing by 3 over 6, I'm just running out of room, so I'm going to kind of cheat here. Dividing by 3 over 6 is the same thing as saying keep the first thing, change 2 at times, and flip the second one to 6 over 3. So that's going away right here. What we're going to be left with is x equals 1 over 2 times 6 over 3. That's going to equal 1 times 6, which is 6, over 2 times 3, which is also 6. Nice thing about this one is 6 over 6 is just equal to 1. So in other words, 1 is going to be our answer for this one. All right, as for this next one, something really weird happens. Once again, you see this minus 2/3. You'd be probably tempted to add 2/3 to both sides, which you can start by doing. But notice real quick right here, if we're adding 2/3 to the right-hand side, these two fractions don't have common denominators. You can't add fractions unless they have a common denominator. So there's no problem in adding 2/3 because that gets rid of our 2/3 here. But there is a problem in trying to do it this way because 6 as a denominator here does not going to add with, or will not add with a denominator 3 right here. So we have to ask ourselves, before we actually finish adding this, how can we change these so that they have a common denominator? Well, the good news is 2 over 3 can be changed to something over 6 just by multiplying the top and the bottom by 2. So this is going to become 4 over 6, which is the same thing as 2 over 3, right? If you multiply the top and the bottom of a fraction by the same number, it just changes what it looks like. It doesn't change what it's equal to. So on this right-hand side here, 5 over 6 plus 4 over 6, that's going to be 9 over 6. So we're going to be left with 5/3 times x equals 9 over 6. And then once again, we just have to divide away that 5/3 on both sides. So if we divide by 5/3 on both sides, this 5/3 is gone. But with this, we run into that classic problem where it's a fraction divided by another fraction. So keep the first one, 9/6 stays the same, change to a multiplying, and flip to a 3 over 5. This is going to leave us with x equals 9 times 3, which is 27, over 6 times 5, which is 30. I feel like this can probably simplify down. Both of these numbers divide by 3. So we can simplify this by turning it into 9 over 10. And I think that's about as far as we can go with that. So 9 over 10 is our solution for x. If you're more of a decimal person, you can change that to 0.9 instead. All right, we're almost done here, folks. Don't worry. We are done. Look at that. There, I thought there was one more slide after this. Haha. Anyway, so for practice, I want you to make sure that you finished page 301, questions 1 and then 4 to 19. This is without a doubt your priority today. That's the one-step problems from last class. That needs to be done no later than the end of today. But once you finish that, of course, I want you to try page 311, just questions 7 and 8. We're going to come back to this again tomorrow. We're really going to be building our understanding of two-step linear equations next class. So at very least, just make sure these are completely finished. And remember, the answers are in the back of the book. And as always, if you have any questions, please let me know.